First of all, thanks to the organizers for the invitation to talk here. I will talk about recent work with Girard-Avedisian and Oleg Evnin, and some of it is based on earlier works. One with that appeared earlier this year with Sukruti Bansal and Oleg Evnin. To start with the motivation for this work, I will mention a few standard things. So electrodynamics is an old subject and it's hard to say something new there, but my motivation here comes from a slightly different place. So we know that in space-time dimensions, T equal to 4ke plus 2 Minkowski spaces, we have a special type of fields, p-form fields that are self-dual. So we can write equations of the form I will assume several things are familiar and will give more details if there are questions, including differential form notations and Hodge dual that is given by the star. So in 2 dimensions, we know that this is there's a self-dual scalar that can be given by equation. And this plays an important role in several sigma models, including in some types of string theory. And in 6 dimensions, we have a self-dual 2-form field whose field strength is a 3-form, and the equations of motion are given in this form. This type of fields are expected to play an important role in several superconformal theories in 6 dimensions, including the 2,0 theory that is supposed to have a non-abelian completion of such equations. In fact, for such systems, writing down a Lagrangian that is, what, sorry? I cannot hear, sorry. All right, sorry. Yeah, exactly. Thanks. So 3 factorial, right? Yeah. Yeah. Signs and factors are very important in this business, but I will be very sketchy about them and sometimes forget about them. But they are all written carefully in the papers, of course. So one, very much related to, so I will mention another important example, which is in 10 dimensions, we have a 4-form in supergravity that, so it's a 5-form field strength satisfies also the self-duality equation. And the problem with this kind of theories is usually that it is hard to write down a Lagrangian that would describe these self-dual fields without violating Lorentz symmetry. And several workarounds of this problem have been known in the literature in the past. And one new type of Lagrangian that would allow for Lorentz covariant formulation of such fields was proposed in the first work, and it can be more or less written in a schematic form as, let's say, I will forget about the factors. Now, F is the field strength of the field under consideration. So let us assume we are in P equals to 4k plus 2, and the P is 2k. So A is a P form, and then such a Lagrangian where we have introduced F as a field strength of the P form, Q as a field strength of another P form, which is auxiliary here, and A is a auxiliary scalar. For those who are familiar with the PST formulation, the field A here plays the same role as the corresponding field with the same name in the PST. There is a simple way to show that there is a equivalence with the PST, especially in the simplest example of 2 dimensions, where one can actually, without any problem, integrate out this fields R and end up with the PST Lagrangian for the 2-dimensional chiral scalar. Now, it is also known that in the case of Minkowski space with the dimension 4k, we have a more or less similar problem of describing the 2k minus 1 form fields. So here we will take form fields that are 2k minus 1 form. There is a similar problem, but related to their democratic description, in the sense that we have electric and magnetic connections appearing in the equal footing, which would mean that we have similar self-duality relations, but for different fields. So these are called twisted self-duality equations. So instead of self-duality, we have duality with another field. Or in other words, one can also write it in the form where epsilon AB is the fully antisymmetric tensor, that A and P take 2 possible values, and we have the equations have SO2 symmetry. So in this case, the same problem arises because naively we don't have a problem of describing the electrodynamics or its analogs in different dimensions in a duality in the Lorentz invariant manner, but this formulation breaks duality symmetry. So in other words, the Maxwell equations can be written in a Lorentz covariant manner in the following form. And one can easily solve one of these equations by introducing the vector potential, and the other equation will follow from a Lagrangian that is written solely in terms of the vector potential. Now, this is one solution, but this solution breaks the SO2 symmetry that the free Maxwell equations have in this form. So if we were to right now, maybe I can continue here. So if we were to now write the free Maxwell equations, they have a symmetry that takes F2 and star F. which is a rotation by an angle alpha in the plane of f and star f. Or in this language, we would say that instead of solving for one of the three equations introducing potential A, one could also solve the other one, introducing another potential. And this system would be described equivalently in the form where we start with the two potentials and just impose the equation that they are dual to each other in the sense of twisted self-duality equations. And in this language, we would have SO2 rotations of the two potentials where now the aim is to describe general theory in the language of both potentials, so that we don't choose one in the favor of the other, and correspondingly that would allow us to have a Lagrangian that we call democratic, in the sense that it treats electric and magnetic potentials in the equal footing. This will actually have its advantages that I will show as we go. And it will also allow to impose the duality symmetry in a more natural manner. So the duality symmetry that the Maxwell equations have, given by those transformations, they are not symmetries of the action given in this form. But if one has a democratic formulation, it can become also the symmetry of the action. And furthermore, the duality symmetric theories are generically, it is hard to find such theories. It leads to equation on general Lagrangian that maybe I should start writing that. So if we take arbitrary nonlinear electrodynamics, the Lagrangian of such electrodynamics given in the standard single potential form is an arbitrary function of two scalars, where S is so these two scalars can parameterize the space of all possible scalars written in terms of F. So I would say that we are taking, and here we are assuming that F mu is curvature of A. So arbitrary nonlinear electrodynamics that has not more than two derivatives in its equations of motion can be written in the form where it is parameterized by two scalars that are given here. We are in 4 dimensions. Now, arbitrary function of S and P.
Arbitrary. Function of function.
Function.
Yeah. You don't allow derivatives.
No, I don't allow derivatives of S and P. It's just the algebraic function of S and P. So in this case, we will basically have the equations that are all given by F's, and there is at least at most one derivative acting. So since F has already one derivative, all of the equations of motion will have not more than two derivatives. So these are a space of nonlinear electrodynamics that has no problems with unitarity.
On S, right? L.
Yeah, it may depend arbitrarily, but on S and P.
The derivative with respect to S must be non-zero.
Yeah, sure. Yeah.
Why sure? If it's an arbitrary function, then not, right?
Yeah, no, I meant that S is still arbitrary, it's given here. So we are not assuming that S is constant. That's what you were asking.
The question was about the class of functions L of two arguments. What is the what is the condition on these functions.
Yeah.
So
It's an arbitrary function.
no, it's not zero, for example. Zero is an arbitrary function. I mean, it's also one.
That is one special case, zero. It could also be, but we are taking it to be an arbitrary function of S and P.
Maybe the question is that for small fields, you would like to recover.
If you want to have some control perturbatively, we would say that for small f's, we would have that Lagrangian is close to S, which is the Maxwell Lagrangian. But in principle, we don't even have to assume that.
Can we just function of P? Can we function of P alone?
Yeah, that is also possible.
And it's not a derivative.
Yeah, but if you have P squared, it's not total derivative anymore. So if it's an arbitrary function of P, it's not a trivial.
Dividing by P and S is prohibited.
What?
Dividing by S and P is prohibited.
No, it's not. It's an arbitrary function that, I mean, of course, in some cases it might make sense only for a certain range of fields, but this is the most general nonlinear electrodynamics I can imagine.
If you take L equal to V, you have no equations of motion. That's fine.
Yes. Yeah.
Don't mind.
That will be some trivial situation.
Maybe what is the question? If you often we want that H symmetries which we insist on to exhaust the H symmetries of our Lagrangian. For instance, if you take Lagrangian 0, it's not a very good theory because it has much more H symmetries than just usual vector. Maybe in your case you want nevertheless some non-degenerate.
Yes, so
Run into this because this should also be communicated.
Most of the interesting results will be applicable only for non-degenerate cases. But for example, there's a specific Lagrangian where you get that it's linear in both S and P, and they come with Lagrange multipliers. So the equations of motion imposed by these Lagrange multipliers is that S is 0, P is 0. This is a very specific type of electrodynamics, which is not perturbative. It's called Pialinsky-Pirula electrodynamics. So in this kind of formulation, we assume that there are no other fields. Therefore, we don't, in principle, we don't have that Lagrangian under control. Because in order to have that Lagrangian, where S and P are 0 by equations of motion, we would need to have two more fields that are the Lagrange multipliers. So this might be not the most general possible case, but it's a sufficiently large class of possible electrodynamic theories. So our aim is now to reformulate this most general function of two variables as a potential Lagrangian of electrodynamics in the language that is making use of both potentials, and this is the concrete aim. And to start with, I will show how this can be done for the Maxwell case, and this comes back to this Lagrangian. So for the free Maxwell theory, we can write down Lagrangian of this form. Let's call this. I will try to avoid using index A because there is a field here, so that there is no confusion. But this is the Lagrangian, which contains, again, as described there. Okay, it's not described there. I will write it. So H is a two form, which can be understood as F plus A Q, where F is a curvature of A, Q is a curvature of R. So in order to use we want to use two potentials A to describe actually a theory that is regular electrodynamics of the one potential. So in order to impose equations that remove the extra degrees of freedom, we actually need to introduce new auxiliary fields, and this is the reason why we have this extra R's here. And so we basically double the field content except for the scalar. So we have altogether 4 vectors and 1 scalar, 17 component fields altogether that describe just 2 degrees of freedom of the 2 polarization of light. So this is the price to pay in order to make the democracy manifest between electric and magnetic degrees of freedom. So
And 1 scalar.
no, we have 4 vector fields. So 2A, 2R, and then so if we do some partial integration and carefully analyze, we can show that fixing some K, one can integrate out these extra fields R, and what we end up with will be the Pasti-Sorokin-Konevich action that contains 2 A's and 1 K. But we will not do that because our aim is to use this now formulation to go to arbitrary nonlinear electrodynamics and show that it works. So there is a way to fill the definition where you basically, so here we have TRF. So we can do some filter definition that allows to bring T in front of this DA and have R appear only algebraically. And then after that, we have to gauge fix R because there are several symmetries that I will mention now that allow to gauge fix R and then integrate it out. And in its equation of motion, it will be only algebraic, so we can integrate it out. We lose the nice polynomial form. We get 1 over TA squared in the denominator, but eventually that will be the PSD. So, and for those who are not familiar, PSD stands for Pasti-Sorokin-Konevich, which is the more or less standard formulation for describing the electrodynamics in a duality symmetric manner, or in other P-form cases, the self-duality equations. So the Lagrangian that was written in mid-90s. So,
How does it look like?
it looks like, let me write it. It looks like this. For electrodynamics, it will be something of this form. If I don't care that much about here. So we have in the denominator the mu A squared. In some sense, this A is the equivalent of that A. It's just we get rid of this denominator by introducing new auxiliary fields R and get a polynomial formulation.
What is the advantage of this?
So I didn't explain more that this F is actually the self-dual combination. So it's basically and the advantage of this theory is that its equation of all of the equations of motion together imply that this F is 0, which implies the duality symmetry equations as written there. So these duality symmetric equations can be derived from the action. In the same way, I will show that they can be derived from this action without any reference to this formulation.
So non temere, the Tonin, the only symmetries are standard Maxwell plus the duality. And the question is whether in this your new formulation, all the additional symmetries that you're introducing with respect to those ones are removed by the gauge fixing that lead.
Well, in some sense, yes, but okay, there are more symmetries here, but they are related to the fact that these new auxiliary fields also have their own gauge symmetries, because they appear in this form, they appear in the only through the curvature. So there are two more U1 gauge symmetries, and there are two symmetries that are there also in the PSD form that I can write down now. So here the symmetries of this action can be given as, of course, there's delta AP equals to T lambda B. This is the standard gauge symmetries, the shift by gradient. There's a delta RP equals to T sigma B. And then again, gradient shift. There is a symmetry where delta A shifts by something proportional to the A. And R correspondingly shifts. So UB is arbitrary scalar now. And then there's the last symmetry, which is very special to, it exists also in the case of PSD, which is it shifts the scalar A with the arbitrary function. So, and correspondingly, the other fields have to shift in some way. So let's see. Let's write the indices to make it clear. And this. So this is a bit more complicated structure of the transformations, but what we need to remember is that
so there is a non-degeneracy condition on the right?
Yeah, so this symmetry makes sense if in these transformations we can do only in the case where the A squared is not 0. And this is the same condition that appears in the PSD.
So A cannot be removed. It's not pure gauge.
In some sense, A can be fixed to be one coordinate, but it cannot be fixed to be 0 or constant. So, yeah. And also in the derivation from our Lagrangian, when we derive equations and then eventually get to the condition that this implies the self-duality equations for the Maxwell fields, we use the fact that A can be gauged to global coordinate. Doesn't matter which one, but this condition is essential in some steps when we. I will mention it.
If you do that, can you go back to the annotated formulation?
Yes, yes. There are two possible formulations basically that are not covariant. In one of them, you gauge fix A to be time direction. In other, you gauge fix it to be space direction. And both of them can be recovered from the section. I think one is annotated one, the other is Schwarz-Zaboronsky, if I'm not mistaken. There are also for specific dimensions other names, like Floriani Chekiev for 2D, that anyway. There's also Zetlin action in 2D, which is related to Floriani-Chekhov. I'm not good with remembering all the cases. But so now it can be shown from this Lagrangian, since I don't think I have that much time to derive it, so I will just ask you to believe me that from this Lagrangian we can derive the equations and show that eventually from the equations of motion it follows that up to some gauge shifts R is 0 and F satisfies this equation. Which is basically the same as what I wrote here, and this implies that we are, even though we have 17 component fields, we are just describing standard electromagnetism, free Maxwell theory. The next point, given the symmetries we know and the free action that we know, it's a natural question to ask whether we have its generalization to interacting cases. And of course, my aim would be one day to understand also non-abelian generalization, but at the moment we are asking about the abelian possible interactions, which is to go to nonlinear electrodynamics. And that we tried to solve, and I will show how. So let me start here. The idea is that we write a more general Lagrangian with the same variables that we introduced and try to make sure that we have as many symmetries as in the free Lagrangian that we have here. So that would impose a condition that in the interacting case we have the same number of degrees of freedom. This is some sort of blind search because it has many loopholes. In principle, it might have led us to some inconsistent examples. But at the very end, when we have the answer, we can look and understand that we found in this language the most general nonlinear electrodynamics, and it is consistent. But first I show what is the way we proceed. So we noticed that there are two terms in the Maxwell Lagrangian. The second term is invariant by itself with respect to first three symmetries given here up to total derivatives at this invariance. And the same is true for the first one. And in fact, we know we can see that this variable h is invariant by itself with respect to the three first symmetries. So the only one that is left is the last symmetry. And what we do is the following. We conjecture that the most general nonlinear electrodynamics can be written as the second term. So I will not care about the indices at the moment and the factors. And we say that now we have arbitrary function of h here. This would be our ansatz for the nonlinear electrodynamics. And the only condition we need to impose is that this last symmetry is also intact in the nonlinear case. Here, using this h, we can construct 6 different Lorentz invariants. So basically, these are given by so when we had only one vector field, there were two possibilities of the contraction of its field strengths, and everything else would be given through those. But here, since we have two of them, there will be basically 4 + 4, 8 invariants, but since they are symmetric, there are only 6 non-trivial invariants. And we will assume that this F here is given through this invariant. Now, the condition that this Lagrangian will be also symmetric with respect to the fourth symmetry imposes 4 linear differential equations on this F. Therefore, its solution is a function of 2 variables that I will show now. So I think I don't have enough time to do it in detail. I'll just give you the answer. So now we will see that FUV is given by there's a sum over the A index here plus arbitrary function of 2 variables, and these 2 variables are and
We impose invariance on the whole?
yes. So this ansatz is already invariant with respect to the first 3. I impose the fourth one.
What is the goal now? I'm lost.
The goal is to find in this language of doubled potentials the most general nonlinear electrodynamics. So a consistent theory of nonlinear electrodynamics, which will generalize this equation, this twisted self-duality equation, to a nonlinear equation.
And one of your requirements is that the symmetries should be all undeformed.
Yes, this is a requirement that would make sure that we don't have extra degrees of freedom. I mean, even that wouldn't be enough as a requirement. It might be that we get a theory, satisfying this requirement, but still not being, still having extra degrees of freedom. But luckily, the end result shows that actually we found the correct generalization of linear.
But it could be also deformed in principle, right? The symmetries, without violating the count.
So our condition is that, so we want to keep everything depending only on the curvatures, so the U1 H symmetries that do not deform. And furthermore, we notice from here that the third symmetry is also automatically satisfied whenever the Lagrangian is given through this second term and arbitrary function of the H mu. Therefore, we just need to take care of the fourth symmetry, and the fourth symmetry, we don't impose that it does not deform. We just want it to be there. But eventually, the most general answer we get, it turns out that it does not deform. So we get a nonlinear theory which has exactly the same symmetries as the linear one.
The last line you replaced by saying just some delta A should be arbitrary, and then you put the same formula for the
our condition is that delta A is an arbitrary function. We don't care what is the rest.
We found the same.
Yes.
Okay, thank you.
So
Sorry. And how with one gauge symmetry do you get the 4 equations?
yeah, that's also a non-trivial statement. So in order for this one gauge symmetry to be satisfied, we need to make sure that from the equations of motion that we get from the 2 vectors, 4 vectors actually, this imposes that. So we want this equation of motion of the field A be a consequence of the rest of the equations of motion. One way to get it, let me quickly write down what it is. So the equation of motion for A so this K is some expression that I can write quickly. So the this K figurates in equations of A and R also. I mean, in their combination, we can actually we get that some combination of equations for A and R of this form: d L d minus A d L d R p is equal to dA which K. Now, in order for this equal to 0 imply that this is 0. Now Q is a 2 form, A is a 1 form. So one way is that to make sure that this implies that KB is 0. This is possible only when KB is self-dual. And this is something we can impose. And this is the way we make sure that the equations of motion of A will be a consequence. It's some just technical trick that actually turns out to be key in this game. So basically this K plays a role of eventually it reduces to the nonlinear equation that replaces the self-duality equation. In the linear case, this K is just this F. So from the equations of fields A and R, we get that K is 0, from which it follows that the equation of A is automatically satisfied on A and R shell, which means that this symmetry exists, because this symmetry already means that the equations of A are not independent of the rest of the equations. So here, the fact that from this I get KB equal to 0, so that this will be satisfied. This is possible only if we impose epsilon BC 0. This is our condition, and given that K is given through this derivatives of F through U, we get 4 equations. First order differential equations on F. And this imposes us that F is eventually just a function of 2 variables. These 2 variables can be understood in several different ways. They can be written through this U and V that I introduced here, but it is actually also possible to take the self-dual combinations of H, and that will give us the lambda 1 as, let me write it here. And the G is So this is one way to see. It's not the most symmetric way, but it's more intuitive. So what we get as equations following from the Lagrangian, where we put this f here, so we get the most general nonlinear electrodynamics that depends on two variables, lambda1 and lambda2, that are given here. And in some sense has the same space as the original LSP that we wrote, because again, function of two variables. And we can actually make connection between the two, which this connection is a map that is a nonlinear algebraic equation that is not always explicitly solvable, but in some examples we can do. And also we can see points where this map breaks. In particular, the above mentions what I mentioned, Bialinski-Pirula theory, that is not possible to write in that form. In this formulation, a democratic formulation, it is possible to write it. The equations of motion basically can be written as this. So again, we can do all the tricks as we did in the free theory. So basically, we can bring it to equations that depends only on the variables a1 and a2, and the r variables can be gauged to 0 using all the equations of motion. And the variable a is a pure gauge again. So eventually we get equations that are only given through this potentials a, and they can be given in this form. So G2 will be derivative of G with respect to lambda 2. Maybe I can write this. And so assuming that G is a nonlinear function of lambda 1 and lambda 2, and lambda 1 and lambda 2 themselves are given through this combination. So we basically can say that this is dg dg. So what we get is that star f1 plus f2 is an arbitrary function. So g prime, let's say, of star f1 minus f2. And one can actually show that this is the most general possible nonlinear completion of this equation, this equal to 0. Because if we need an equation that would give an algebraic relation between star f1 and f2, we could basically use a basis where star f1 plus f2 and star f1 minus f2 are independent tensors. And in the right-hand side, whenever star f1 plus f2 would appear, we would solve the equations to find this algebraic relation. It just happens that the ansatz that we chose automatically gives us it in this form, which is some sort of preferred basis of field redefinitions. Okay, and the next point that I want to show is the relation with the standard nonlinear electrodynamics. This is something we can do in the following form. Now, given these equations, we can try to solve f1 in terms of f2. And what we get is that eventually we can write, given that this is a regular theory that it is possible to solve F1 in terms of F2, which is possible in almost all cases, except for zero measure space. So we can come to such an equation. And now if we take an external derivative of this F1, we will get an equation given only by the second potential. And this should match the equation that we would get from the Lagrangian with a single potential. And here S would be F2 squared, and P would be F2 wedge F2. So, so this would imply that alpha, in order to make contact with the standard nonlinear electrodynamics, we would get alpha SP is equal to minus dl dp, where L is that LSP that is written there, and beta SP would be dl ds. For this is a work in progress, but I can already report that for sufficiently regular theories, there is always a solution. So if we have this form of the theory and get the equations here, there's always a possibility to find corresponding Lagrangian, because in principle it might be non-trivial in the sense that this alpha and beta here would satisfy the condition that come from the same function, two different derivatives of the same function. This is a very non-trivial condition. And vice versa, once we have a standard nonlinear electrodynamics, if we want to go to democratic formulation, we have to get the similar equations that I will write here. And that would that might not have solutions in general, but for sufficiently regular theories, it will have. So the conditions that we get is that G1 is equal to alpha squared plus 1 squared, and G1 is the derivative of G with respect to lambda 1, and G2 is the derivative of G2 with respect to lambda 2. And the next non-triviality is that lambda 1 and lambda 2 themselves will be given through alpha and beta and S and P. There are some notations where this even simplifies more, but I will not go there at the moment. Next thing is that if we want to impose on top of the so we found the most general Lagrangian for nonlinear electrodynamics without any additional symmetries. Now we want to impose extra conditions of symmetries. One natural thing is to impose the duality symmetry. That was the original motivation, the starting free theory of electromagnetism that could be given in this form as in the equations of motion. It has the duality symmetry that rotates as given here. And in principle, imposing this symmetry will restrict possible forms of the Lagrangians that we have there. And I will quickly review what happens when we impose duality symmetry in the case of standard electromagnetism. So if we introduce new variables, this will be simpler to write. So in these variables, now I can write nonlinear electrodynamics as LUV. and the duality symmetry, that is also called the Gilliard-Zumino-Gibbons-Rashid condition on this Lagrangian, would be what?
Too much down.
What, sorry?
It's, can you push it up?
Sorry.
The condition on this Lagrangian is that dul dvl equals to, it depends on some notations. I think it should be -1 in this notation, in this definition. This equation appears in the very old book by Courant and Hilbert, and it can be solved through the solution is not really explicit. So there is a non-explicit function in the solution, and rare examples are known where one can actually explicitly write the Lagrangian for such theories. Some of the rare examples were actually found very recently, just last year. I will mention that too, but first I tell you what would be the duality symmetry condition in the language of the formulation I mentioned here. So we have the Lagrangian that is given as you might have noticed, this is actually the first term here. So what we get is that general Lagrangian of nonlinear electrodynamics, let's say democratic nonlinear electrodynamics, is the Maxwell Lagrangian, democratic Maxwell, plus arbitrary function of two variables. So there are several duality symmetry conditions one can impose. One of these is that we can impose not the full rotation by arbitrary alpha, but rotations only by multiples of pi half. In that case, we would get the discrete duality, and that rotation will take g lambda 1, lambda 2. So this one is invariant to g minus lambda 1 minus lambda 2. So if we impose that these are equal to each other, this describes the theories with discrete duality symmetry. Now, if we want more than that, we can impose the most generic rotation with arbitrary alpha, and we actually can notice that this rotates lambda 1 and lambda 2 as a vector in the two-dimensional plane. Therefore, this transformation leaves invariant the length of this vector. So if we introduce w is equal to square root lambda 1 squared plus lambda 2 squared, then the most general duality symmetric Lagrangian, let's say duality symmetric democratic nonlinear electrodynamics, will be given as democratic Maxwell plus arbitrary function of w. So it's given through a function of one variable. It is true that also in the standard formulation, it is known that the space of functions with the space of Lagrangians with duality symmetry is parameterized by a function of one variable, and here we get explicit Lagrangian of that form. So giving arbitrary function here, we generate an example of a duality symmetric theory, which is non-trivial in the other formulation. Another point I wanted to mention is that we can also impose another symmetry, which is conformal symmetry, and this would let's say this is the duality symmetry. Leads that g is actually a function of one variable, and conformal symmetry does similar job. It says that g is actually lambda 1 times a function of lambda 1 over lambda 2. Again, we get that we have parameterized all conformal theories of nonlinear electrodynamics by a function of one variable. But then when we impose both of these conditions, then this fixes all the functional freedom, conformal symmetry. Then what we get is that this function HW has to be actually a linear function. So it's just a constant times W. This gives us a one parameter family given by the arbitrary number delta. One parameter family of theories that are both duality symmetric and conformal invariant. This is the such a one parameter family was found a year ago by Pandos, Lechner, Sorokin, and Townsend, and they called it modified Maxwell, ModMax. And there was another example known since a long time, which is the Bialinitsky-Pierula electrodynamics. So using this map that I showed here, once knowing the theory in this formulation, we can rewrite it and bring it to the form where we have just regular nonlinear electrodynamics. Using this map, we can make a contact. So modmax Lagrangian would be recovered from our construction for delta equals to tangents hyperbolic gamma over 2, if I remember correctly. I can check. And so this gamma appears as actually it's cotangent. This gamma appears in the modmax Lagrangian, which I will write here in the regular form. The modmax is given as minus push gamma plus sinh gamma root squared plus p squared. And this does not involve the case where delta is equal to 1, which we show that leads to Bialinitsky-Pierula electrodynamics, which cannot be written in this form, or in the Lagrangian form with one potential. It requires two more auxiliary fields. So this lambda and mu are auxiliary fields that impose the equations S equal to 0 and P equal to 0, where S and P are given there. So this would be the PB electrodynamics, but this is not in that form of just depending on S and P. Therefore, this map doesn't work in that case, but we can show that our formulation with delta equal 1 leads to the same theory. I will stop here, but I can give another example if you are interested. Pornefeld is an interesting example that I didn't have time to show.
So let's thank.
Some questions?
The question, general type. So maybe it's already what you said. At the point you mentioned that, so you want to impose a set of symmetries. Then you construct the most general Lagrangian or general Lagrangian respecting the H symmetries, which in principle should imply that degrees of freedom are not more than the one we started with, although you said that this is not for granted.
Yes, so I don't have a theorem to show that if you start from a theory, you deform it in a way that you have the same gauge symmetries.
The symmetries, and the equations of motion are of the same order. If you keep the symmetries, gauge symmetries, and the equations of motion are of the same order, I would say you at most you would have less degrees.
Usually.
But I would say you have the same number of first-class constraints.
Yes, that's our aim.
And the order of equations is not increased. This is also a condition. In this case, I would say, yeah, there is a theorem in the sense that at most by deforming your theory, you could introduce additional constraints without noticing. So maybe you have less degrees of freedom. But having more, to be honest, I think is.
Yes, I would say that I was already cautious in stating statements, but in the sense, eventually, once we get to the last answer, we see that everything is consistent. So we don't need to worry about. But to start with, it's kind of a blind search. Is this the most general thing we are doing? I don't have a full answer to that. At least I don't have a theorem that this is the most general thing that can be done. But eventually, we see that we get actually the most general possible equations that could deform the standard twisted self-duality equations. About imposing more symmetries, I meant, of course, duality symmetries that are not gauge symmetries to start with. These are global symmetries. So imposing these symmetries, as I mentioned, is either we impose the discrete duality, which is easier. It is still staying in the space of functions of two variables. But when we impose, it's just even functions in some sense. But when we impose the continuous duality symmetry, then we increase the number of variables by one. So we have the most general duality symmetric theory given here is the function of one variable, and in the conformal symmetry does the same job, but in a different directions. But if you impose both, then the functional freedom is gone, and we have only one parameter left. And so there could be one extra symmetry imposed. It actually turns out that in this case, when delta is equal to 1, the symmetry of the theory increases from SO2 to SL2. So this is the most symmetric electrodynamics one can have. It's Batalin-Vilkovisky theory. And if you allow me, I will write also the case of Formulation. So when we derived this, so getting that the most general duality symmetric electrodynamics is given by a function of one variable. The natural question arises: what is the function in the known cases? Because we know that some cases that we know are very interesting for many perspectives, like the Formulation theory, and it would be nice to understand for that case what is this function. And it was some kind of disappointment, at least for me, that it's not a very simple function, but eventually we managed to find an implicit description of this function that is nice. So we can write it in the form that so W is function of lambda, H is function of lambda. If we invert now lambda in terms of W and put here, then we will get what should stand here for the Formulation theory. And this is take half an hour if I write explicitly, but this format is this one.
Okay, so are there any other questions? Yes.
The non-abelian analog?
I hope so. That's the aim. I mean, but we don't know any example of deformation of this duality symmetry to non-abelian. In principle, the advantage of this formulation, in my opinion, is that we are able to describe also theories that are not duality symmetric, but the most general electrodynamics. And in principle, this has enough room to capture also non-abelian theories that might break duality symmetry. So the idea is to find the democratic formulation of non-abelian case, and I believe there is no theorem forbidding it. There are many theorems forbidding the duality symmetric non-abelian, but even not duality symmetric non-abelian can be written in a democratic form. That's what I hope. So this formulation can be the starting point for such research. Of course,
Maybe a remark.
We have Young's theory that satisfies all of it. What do you want more? I think, I mean, Bordy theory is just a toy example in principle. There are examples of, for example, 62 form that eventually we hope to find a non-abelian theory for those. And the technical complications are similar to the case.
Maybe a remark, I mean, these PV techniques are quite adapted to such type of questions, right?
Yeah.